Hello, this will be another video for the really best first search. This will be raising GBFS, GBFS or really best first search. That is technically a informed search algorithm that prioritizes nodes closest to the goal using a heuristic function HLN, which estimates the cost from node n to the goal. So it is called really because it selects the most promising node. So from I mean promising node at each step without considering path cost, which can lead to suboptimal solution. It is suitable for applications like game AI or navigation where near instant results are critical. So in this case, class, at each step in the greedy best first search, we select the node with the lowest heuristic value under the assumption that this node is most likely to lead that goal, to lead that to the goal that you are looking for, or the element that you're searching, or the goal that you're searching. Unlike the A-star search, it will be different because we'll be going to consider the G of n and the H of n. We'll be going to illustrate the specific example as well. So in read best first search, it does not consider the cost to reach a node, which is the G of n, which will be need to apply the extras are going to be a star, but what's different here is commonly the function of the H of n. So it only consider the estimated cost from the node to the goal only. So GPFS is heuristic driven algorithm ideal for scenarios requiring rapid solution action. So, but anyway, it sacrifices optimality and completeness for speed. So its effectiveness hinges on the heuristic quality, making it suitable for applications like the game AI or navigation where near instant results are critical. So in this case, class, the steps will follow initializing, node selection, goal checking, expansion, repeat until the goal is found or the queue is empty. So you are actually using a queue here, but technically I don't want you to deal with a queue anymore because I don't want you to have a lot of writings in your examination. So I'll begin to just want you to, because you will insert that in a queue structure, so it will be a long process. So here then, technically here, node selection, remove the node with the lowest HVAN value from the priority queue. Since in your priority queue, you will be going to insert that in a queue, for example. So technically, um, you will definitely do this step by step process. So remove the node with the lowest HVAN value from the priority queue. This node is considered the most promising candidate for reaching the goal. So meaning, those low priority. Those are, I mean, the lowest HVAN or the lowest, that is the high priority in this case. Those low value, those are the lowest element. Those are the high priority in this case. So this node is considered the most promising candidate for reaching the goal. Those are the, if it's somewhat low, if you're using the low priority queue, so those low elements will be removed first in your queue data structure. So the code chart, if the selected node is a goal node, the search terminates successfully and the path can be reconstructed. So what will then happen here if you were able to find the goal already? So you will just stop the algorithm. And the expansion generate all successor neighboring nodes of the selected node. That means to say that you will be able to include that in your array, I mean your queue. For each successor, calculate its heuristic value, h of n. The successor is not being visited or is not in the priority queue, and add that into the queue. Or you add that into the queue already. Now repeat these steps 2 to 4 until the goal is found or priority queue is empty. So what will happen? You will begin to repeat that one until you were able to find the goal already there. So the time complexity depends on the branching factor as the B is equals to the maximum number of successors per node, and the depth D is equals to the depth of the shallowest goal node. In this matter, for the time complexity, that is definitely start with the initial. what I call this one, we'll begin to start with the initial node in a particle, which is um h of n. So we'll begin to see that later on. Number of nodes, that is the n, total nodes in the search space. So that will depend on those particular cases that right there that we did have. So in this one, the best search that we'll begin to determine, that is this here. Best case is constant time, meaning goal is found at the start or the rare case. I mean start node. So that is absolutely a rare situation here because, for example, in your tree or in your, what we call this one, in your um in your graph or in your tree, that is the first item or the initial state. So it will be rare that go. So the average case will be the annotation of B of D. When we say B, that is the branching factor, and D, that is the depth. So that will depend on the one. Explorers, clumsy news, basically risking may visit many irrelevant class. So first we are searching a lot of irrelevant adjacency of that. So for this here, the worst case is still the annotation of B to the power of N. In worst case, a bond erase that it may behave like the breadth first search and explores the entire tree where you're able to exhaust everything step by step. Oh, that is totally insane. Now, space complexity will be the annotation of B to the power of D. When we say to the power of D, that is your depth. So, that means to say, like the breadth first search, it will store all nodes in memory that are in the frontier or the priority queue based on the age event. Need space for priority queue for frontier and visitor node example checking. So that's how it works in the space complexity as well. So we need to illustrate as well the example for that one in the next video. How will we able to work on that one step by step procedure as well. So thank you and see you in there.